Operators. These we're talking about the things that you use to create new observables by applying some logic to them. So in this case, we're just for the easiest scenario is the map operator. I feel like everybody really understands the map operator, could write the map operator if they needed to. So we're just going to go through how the map operator is written before. Now, when you write the map operator, you need a couple things that are left out right here. You need a reference to the argument, the project argument. You need to use that inside the operator. You need a reference to the source observable that you're going to be mapping its values through. You need a destination observer, like sometimes called a sink, that we can send those map values to, and then we need to return a new observable instance. This is pretty much the 4 or 5 things that we need in any operator. We have the arguments to that operator. We need a reference to the source observable somehow. We need a reference to the destination observer when you subscribe. We need to return some sort of result observable, and then we obviously need to do whatever that operator is supposed to do. So you can think about it in all the versions of Rx before this one, and most of the versions of Rx in other languages. All of the operators can be genericized as variants of flatMap. If you think of map, really that could just be calling flatMap and always returning an observable of 1, right, with the map value. So flatMap has the signature where it takes a projection function, and for each value, you return an observable of a new type. So if this were filter, you could write that as a flatMap that looks at the value and either returns observable.empty or observable.of1, right? So all of the operators could be implemented in terms of flatMap, but that's not very efficient. If we implemented all the operators in terms of flatMap, we'd write a whole bunch of extra code and then also create a whole bunch of inner observables that we just kind of have to unwrap at different times. But what we also have is that we also have a lot of closures. And when we originally started with RxJS 5, we started with the performance in mind, and we wanted to eliminate a lot of the things that we saw as performance problems. And closures and closure state was definitely one of them. So then, as we were starting up, Eric Meyer gave us a really good idea, was to change the base function sort of that everything is implemented as, or in terms of, and implement it in terms of lift. Lift has a very similar signature to flatMap, but it's different in a few key ways. Is lift still transforms from one type to another type, and it still takes a project function, but whereas flatMap takes a value of one type, of the input type, and returns an observable of the output type. Lift actually flips that around and then also changes the incoming and outgoing types. The first thing it does is it takes an observer and returns an observer, but more specifically, it takes an observer of the output type and then returns an observer of the input type. So whereas flatMap would take a value of the input type and then return an observable of the output type, this takes an observer of the output type and returns a different observer of the input type. And it seems a little backwards, but.
Where does the name come from, lift? What is...
Lift is actually, it's actually fmap, right? Like it's map. And so this is, we've called it lift specifically because we didn't already have lift in Rx. And we also didn't want to call it map-L or lift-M. But it's pretty much just map. In this case, so observables, they have like an inner type, and this doesn't work on the inner type, this works on the wrapper around the inner type. So that's another reason we went with lift. So here's how we'd write map using lift instead of flatMap. I had an example where we were using flatMap, but since no one actually implements map in terms of flatMap, it wasn't as useful. But we do actually implement map in terms of lift. In fact, all the operators are implemented in terms of lift. So if we were writing our observable class, we have our map function, which takes a project argument, and all we have to do is return this.lift and pass it a new map operator, where we pass the project function to the constructor of the map operator. Here's the map operator right here. It's a pretty simple class. It takes the project function in its constructor, and then it has a call method And the call method was named call for a very specific reason, because we also wanted operators to potentially be functions. So we just wanted to map the function API. So if you could use just a naked function as an operator, or you could create a strongly typed operator as a class. Either way, they both have call methods, and they can take these two parameters. So when this call method is called, it's passed the destination observer and the source to subscribe to, and then it's supposed to subscribe to the source with the specific observer type. In this case, a map observer. And so here's the map observer that gets created whenever you subscribe to a mapped observable. And as you can see inside, it just has a projector for the destination and or as a constructor for the destination and the project function, and then when it next values, it just passes on the projected value. Obviously, there's a little bit more to this. Most operators have like try-catch handling inside. They have early completion stuff, but this is really just the basic foundation of how these operators work. And what this really does is we're really just defeating the virtual machine here. What this architecture does is it gives us predictable shapes rather than having the closure state, rather than accessing our values through the closure state, where the VM would have to create anonymous inner classes in the best case. We're explicitly creating those classes for it. So every time we return, the VM can predict the shape of the object we're going to return and optimize lookups. And another important thing is that we're always ensuring hot code paths are taken. So since all of the subscribers extend the base subscriber, they just do their little bit of logic and then kick it back up to the base class. So as long as we can make sure that the base classes methods inline well, and we can even reduce more code inside there, then we can speed up the entire library for everybody. What this also allows us to do, which is sort of unrelated to the operators themselves, but doing it this way allows us to merge the observer and the subscription type. So rather than having a pair of subscription, which represents the thing that was returned from subscribe, and the observer, which is the thing that you created to subscribe, we can actually merge those two together in a single instance and just have one instance instead of two. So we save on allocations that way. And this is probably my favorite, is that we can customize the observable type that gets returned. So something you could never do before, if you in Rx wanted to like extend the observable, create your own API, well, you could do that. You could extend observable and add like an operator to it. Let's say that mapped from world coordinates to local coordinates. I don't know. Well, as soon as you called flatMap on that, you'd be screwed. It would give you back the base observable type. Pretty much calling any operator would give you back the base observable type for the reason right here is all the operators are implemented as when you call them, they return a new observable strictly. That's just what they did. Well, in the new way, since all the operators call this.lift, by extending observable, you can override lift, take in the operator, and return the subclass that you desire, right? The static functions are a little harder to do, but you can do that too if you loop over and override all the static functions. But this is pretty powerful because maybe I'm the only person in the world who does this, but it's pretty cool. You can write your own DSLs based on observable and still have them be observable. So you can concatenate two gesture observables together and get out your gesture observable. Concatenate two file system observables together and then do a write file for your file system observables. So that's something that I find useful, but maybe an advanced feature. That's pretty much it for the operators. Does anybody have any questions on specifics?
What was the performance problems that like in a practical sense? It seems like I don't know, I'm not like streaming digits of pi in RxJS.
Right. Oh yeah. So what were the specific performance
problems? It made a lot of
problems?
sense in like the server side, like where like RxJava, like then you kind of aren't, you care about like these very small performance gains because multiplied by end users, this is a big deal, but like,
Right.
I don't know.
No, that's a
This
fair
is
question.
an honest question, like maybe there is something that like
Yeah. That's a fair question. The question was what were the performance gains specifically, and why were they problems before, before version 5? And I think we first started from the idea that it's going to be used in Node, and it's going to be used on the server. So if people aren't familiar, a project that uses it is the Falcor router, which is an asynchronous recursive route matching thing. That's kind of got some similar design requirements as some of the Rx Java stuff. But even in the browser, I came into a project probably a year and a half ago with the place I work. Just upgrading from 4 to 5 was, now given we use a lot of WebGL and there's a lot going on, but just upgrading 4 to 5 made a noticeable difference in things like our mouse input handling and lag. Maybe it's not a perfect example because we do some high performance stuff, but we've got this basically a big video game loop where between the client and the server. So we're constantly running like n-body simulation ticks on the server, and we need to sort of get those events in and pump them through as fast as possible and run a big physics simulation on the GPU, and then pump those events back out and we compress them, send them down to the client, and then do all of that again pretty much as fast as possible. I think when you combine it with lots of other things happening concurrently, because this isn't the only area that we tackled for performance, we also tackled the schedulers. And so especially when you throw in the schedulers, if you've got a lot of observables using a lot of scheduler stuff, then you're sort of spiking allocations, and it's hard for the VM to figure out when it's safe to garbage collect. So overall, reducing the memory pressure on the VM was really important.
And just to circle on that, at Netflix, I maintain an app that sometimes has 200,000 requests per second coming to your browser. And so those little tiny allocations that you could make that are very short-lived can cause garbage collection pauses when you do those type of things, when you have very high volume coming to the browser. Sure, a lot, if you're just making click handlers and not really doing anything high performance, then it's not going to be, you wouldn't necessarily notice the difference. But there's a lot of scenarios that Rx because Rx can be used for anything, but it shines the most when you're dealing with high volume things. That's kind of one of our goals, is to be very performant. So.
All right. Ready?
Round of applause.
Hey there, are you into reactive programming using JavaScript? Do you have to deal with asynchrony in your web app? Then join this instructor Ben Lesh to learn all of the ins and outs of RxJS in his hands-on workshop. Available online and in person, go to rxworkshop.com for more details and to book your spot today.